Okay, everybody. Welcome back to the final part of the 2017 AP Calculus AB review. So we left off in question number 5. And in question number 5, we have the region R in the first quadrant enclosed by the graphs of f of x and g of x, and the vertical line x equals pi over 2. Right, but do not evaluate an integral expression that gives the area of the region R. Well, as you guys know, if you want to find the area of a region, you're going to have to do the integral from a to b of the top function minus the bottom function with respect to x. So that means that we're going to go from 0 to pi over 2. And the top function here is e of x minus the square root of cosine of x dx. Okay, and that's about it. Part B. Find the volume of the solid generated when r is revolved about the x-axis. Okay, when r is revolved about the x-axis. So let's take a look. The graph itself looks a little something like this. And when you revolve it about the x-axis, the point right here, the y-intercept 1, is going to be reflected all the way down to -1. We're going to have a line here, revolved, right? This is basically e to the x. And then we have the square root of cosine of x. Now, as you revolve it, we're going to be getting an outer circle, and then we're going to also get an inner circle with a gap. Okay. So the volume of the solid is going to be the integral from a to b of pi r squared minus pi r squared dx. We're using two areas of a circle because again, when you revolve this, we're going to be getting a solid where the big circle is the solid and then the small circle is the gap. So the volume equals the integral from 0 to pi over 2. You know what? We're going to go ahead and take out the pi to the outside of the integral since it's a constant. The big radius is given by e to the x, since you can go from the x-axis all the way to the top of the function, right? Represented by e to the x minus the small radius is the length between the x-axis all the way to the first function, which is the square root of cosine of x. So then we have the square root of cosine of x squared dx. And again, if you're still confused about how to identify the big radius and the little radius, the first thing you need to do is identify the center of the circle. Take your pencil and then just move it straight up, and whatever function you hit first, that function is going to be the little radius, and whatever function you hit second, that's going to be the big radius. All right. Okay, well, let's keep going. Pi times the integral from 0 to pi over 2 of e to the power of 2x. Right here, remember the exponents multiply, right? It's not going to be x to the power of 2 minus cosine of x dx. The square root and the square cancel each other out. The volume equals pi. And now we can go ahead and find our antiderivatives. The antiderivative of e to the 2x is 1/2 e to the 2x. And I told a couple of you this little trick. Think about taking the derivative of e to the 2x. What do you get? You're going to get e to the 2x times 2. So when you're taking an antiderivative, you can think of the same way, but instead of multiplying by the derivative of of u, we're going to call this u, you're going to multiply times the reciprocal of u. Well, times the reciprocal of the derivative of u. So in other words, if you're trying to integrate e to the power of 3x, you're going to get 1/3 e to the power of 3x. If you're trying to integrate e to the power of 1/2 x, you're going to get 2 e to the power of 1/2 x. Right? So you're always taking the derivative of u, but we're using the reciprocal when doing antiderivatives. And if all that confuses you, then just go ahead and do u substitution, where u is equal to 2x, du dx is equal to 2, du is equal to 2 dx, 1/2 du is equal to dx. So then this integral becomes e to the u times 1/2 du. Thus, the antiderivative is 1/2 e to the u. Okay, the antiderivative of cosine is sine. And all of that's going to be evaluated from 0 to pi over 2. So then the volume equals pi 1/2 e to the power of 2 times pi over 2 minus sine of pi over 2 minus, in parentheses, 1/2 of e to the 0 minus sine of 0. So we're going to go ahead and simplify this one step at a time. First, the exponent of e becomes pi. Sine of pi over 2 is 1. E to the power of 0, well, that becomes 1. That's going to leave us with a 1/2. And sine of 0 is just 0. So now we have pi 1/2 e to the pi minus 3/2. And that right there should be our answer. C. The region R is the base of a solid whose cross-sections perpendicular to the x-axis are semicircles with diameters on the xy plane. Write but do not evaluate an integral expression that gives the volume for this solid. A ver, miren. So here's region R again. Nice, region R. So now, dice que the base of the solid has cross-sections that are semicircles. So think about semicircles sticking up. So here's the diameter of the semicircle. And then here's the semicircle sticking up at you. Diameter, semicircle. And it's kind of harder for me to draw three-dimensional shapes, but hopefully you get the idea. So if we're going to find the volume, as you know, we're going to go and take the integral from a to b of the area of the cross-section, which in this case, you know what? Let me write this. A of x dx, where a of x is the area of the cross-section. The limits of integration are still 0 to pi over 2 because those have not changed. We have half circles, so the cross-section is going to be 1/2 pi r squared. We just have to figure out what the radius is. Well, this distance is the diameter, and that distance is given by e to the x minus the square root of cosine of x. So if you want to take the radius, then you're going to have to get half of that. So the integral from 0 to pi over 2 of 1/2 pi times e to the x minus the square root of cosine of x over 2 squared dx. And you can go ahead and leave this like that, but you could simplify it a little more. We can take the pi over 2 out of the integral since it's constant. And I don't want to FOIL out the expression that I have in parentheses, but what I can do is square the denominator. 2 to the power of 2 is 4. And again, you can leave it like this, or you can leave it like the previous step. This is good. This is good. And if you wanted to simplify it even more, you can take out the 1/4 out of the integral. And this one is good. All three of those should be fine. Question 6. For 0 is less than or equal to t is less than or equal to 6 seconds, a screensaver on a computer screen shows 2 circles that start as dots and expand outward. At the instant the first circle has a radius of 9 centimeters, the radius is increasing at a rate of 3/2 centimeters per second. Find the rate at which the area of the circle is changing at that instant. Indicate the unit of measure. So this right here, we're talking about related rates. Since we have a dot, and then it extends as a circle, which means the radius is increasing, and the area is increasing, the circumference is increasing, and as you keep extending the circle, everything is increasing, right? So we know at the instant the radius is 9 centimeters. The radius is increasing at a rate of 3/2 centimeters per second. And we want to find the rate at which the area is increasing. Find the rate at which the area of the circle is changing at that instant. Well, we know that the area of a circle is pi r squared. So if I take the derivative, I'm going to get 2 pi r times the r dt. And we get this because we apply the chain rule, right? You take the derivative of the outside. Oh, wait. That wouldn't make sense. You take the derivative of the outside. You leave the inside alone. So this one just comes back down. But then you multiply times the derivative of the inside. So the derivative right there would be the r dt. Okay. Well, we're looking for the dt. We know the radius is 9, and we know that the r dt is 3/2. So this becomes, let's check it out. The 2 will cancel with the 2. Thus giving us 27 pi centimeters squared per second. The reason why the units are centimeters squared is because, well, the r dt is centimeters per second and r is centimeters. So then when you multiply them, you get centimeters squared. Plus, we're dealing with area here, ¿verdad? And area is units squared. Okay, part B. The radius of the first circle is modeled by W of t from 0 to 6 seconds, where Wt is measured in centimeters and t is measured in seconds. At what time t is the radius of the circle increasing at the rate of 3 centimeters per second? At what time is the radius of the circle increasing at a rate of 3 centimeters per second? Okay. So we know since the radius is represented by W, we know that dW dt equals the rate of the radius, which we know to be 3 centimeters per second. Okay, but what we want to actually find is the time, right, when this happens. So we'll go ahead and find dw dt. dw dt is going to be negative 12 e to the power of negative 0.5 t times the derivative of u times the derivative of the exponent, negative 0.5. From here, I can go ahead and say that dw dt is equal to 3. And I can also go ahead and simplify. The negatives cancel each other out. The 12 and the 0.5 make 6. Well, next, divide by 6. Take the natural log. Divide. You know what? This negative 0.5, you can think of it as negative 1/2. So what we can do now is multiply by negative 2. So negative 2 natural log of 1/2 equals t. And this right here, that should be fine. It should be enough for your answer. But I do see that in the solutions, they simplify it even further. And this is extra, okay? This should be fine. But if you want to take it a step further and realize how the solutions show the answer, well, what you can do is take the negative and move it to the inside of the logarithm, right? That's one of the logarithm properties. The negative can come inside and become an exponent. And what the exponent does, it makes you flip the fraction into a 2. It makes you get the reciprocal. So this right here is an even better simplified answer. But you know what? I should have done this at the same time. Using the same property of logarithms, I can bring the 2 as an exponent and call it the natural log of 4. So at what time t is the radius of the circle increasing at a rate of 3 centimeters per second? At natural log 4 seconds. The question doesn't ask me to justify my reasoning, right? So I'm not going to write a sentence. But that's what it is. As long as you put your units, you should be fine. And finally, C. A model for the radius of the second circle is given by the function f from 0 to 6 seconds, where f is measured in centimeters, t is measured in seconds. The rate of change of the radius of the second circle is given by f prime. Based on this model, by how many centimeters does the radius of the second circle increase from 0 to 3? Okay. This question is asking me to find total change, right? Because we know the circle started as a dot, and then it increased to a circle, and then it increased to a bigger circle, and then it increased. So this question is not just asking about change, it's really asking about total change. How many centimeters does the radius of the second circle increase? So for that, you're going to take the integral from 0 to 3 of the absolute value of f prime of t dt. So you can write it as the integral from 0 to 3 of t squared minus 4t plus 4 dt. We can actually take off the absolute value because from 0 to 3, this function is strictly increasing. It's a parabola with a y-intercept of 4. So when you plug in 1, you don't have to graph it, right? This is just for me to show you that it represents a function that is strictly increasing. When you plug in 1, you get 1 minus 4 plus 4, which is 1. When you plug in 2, you get 4 minus 8 plus 4, which is actually 0. When you plug in 3, you get 9 minus 12 plus 4, which is back to 1. Now, don't forget that this equation represents a derivative. So even though you see a decrease in it, you shouldn't be looking at a slope. You should be looking at the value, right? F prime of t is greater than or equal to 0 on 0 to 3. And that's why we don't have to worry about the absolute value, because the change is always positive. So let's just go ahead and do our integral. So the integral is 1 over 3 t to the power of 3 minus 2t squared plus 4t evaluated from 0 to 3. This becomes 1 over 3 times 27 minus 2 times 9 plus 12 minus 0. This is 9 minus 18 plus 12, which is 3. So how many centimeters does the radius of the second circle increase from 0 to 3 seconds? By 3 centimeters. Now, you know what? Maybe I should have done a sentence in the last one. The radius of the second circle increased or increases by 3 centimeters from 0 to 3 seconds. And let me go back and fix my other one just in case. At time natural log of 4 seconds, the circle's radius is increasing at a rate of 3 centimeters per second. There we go, just to be safe. And that's it. Thank you very much for checking out the video. Remember, guys, that I'm gonna be in school at 7:30 a.m. on Tuesday. And the Saturday when we come back, we're gonna take another AP test. That's gonna count as a quiz. It's gonna be out of 40 points. So make sure to study and study and study those FRQs. Okay. Well, thank you very much. Have a good break. I'll see you soon.